in this video, we're talking about rates of change, also tangent lines to curves, but we're starting with this really important fundamental idea of calculus, and it's the rate at which something is changing, and that's something that we look at so much and in so much detail when we are talking about calculus, and specifically we'll learn the derivative. So we have the idea of an average rate of change and also an instantaneous or at a moment's rate of change. And so we're going to start with average and then move our way to instantaneous. But this idea is so fundamental and it's widely applied. We're always thinking about rates of change. How fast is the car traveling and the distance changing based on that? How much is my investment account growing with the money and the interest rate? How quickly am I burning calories when I work out at the gym? There's so many applications to this idea. So we start with average speed, and we have a formula for that. And the average speed is distance over time. So how far you traveled over how much time has passed. And so the formula is that you take the two distances and you subtract them. So you say, well, where did you stop minus where did you start? And you do the same thing for the time. So the stopping time minus the starting time, and that will give you the time that has passed or elapsed. So the formula, you have to have some kind of formula to plug in the times to, T2 and T1 you can see here, to be able to give you this distance traveled. So for us, this first example, you have a rock that breaks loose from the top of a cliff. So a rock is falling. And so the formula that we would use here for F, it would be our free fall formula. And it is F of t, so some function of time passing. Imagine the object is falling, so as time passes, that distance changes. And it's going to be 16t squared. And this is if you are measuring your distance in feet. If you're measuring your distance in, let's say, meters, then this formula would be 4.9 t squared. So this has to do with an object falling where the only thing really acting on that object is gravity. So what we want to know is during the first 2 seconds, what is the average speed? Okay, so first 2 seconds means we need a starting time and a stopping time. So our starting time, if it's the first 2 seconds, well, we're starting at time 0. And we want to just notice that we are dealing with seconds. And our stopping time would be T2. It's going to be at the 2 second mark. Okay, so we would go to our formula, which is difference in the distance over the difference in the time. So we're going to plug this in. F of T2, which is our 2 seconds, our stopping position, minus F of 0, our starting position, over the stop time minus the start time. So we know that 2 seconds has passed, so that's the time elapsed on bottom. And for the F value, the function value, we actually have to plug in these inputs, these time values. So we have 16 times 2 seconds squared, and this will give us an amount of feet, minus 16 times 0 squared. And so on top, if we work this out, that's going to be 4 times 16, so 64 minus 0 over 2. So this simplifies to 32, and the units was feet. And remember, this was feet per second, so this is feet per second. And there's an invisible 1 on the bottom if you think about it, because we divided 64 by 2, so it's 32 divided by 1. So it's 32 feet for every 1 second. So that is our average speed of our rock falling. So now let's do the next part. We want to know the average speed during 1 second interval between second 1 and second 2. Our start time is 1 second, and our stop time is second 2, so T2 is 2. So 1 second has passed, and we want to know the object started falling, and then we start calculating at the 1 second mark, and we stop calculating at the 2 second mark. So we plug right back into our formula. F of 2, our stopping position, minus F of 1, our starting position. The time that has passed was 1 second, but you can get that by saying 2 seconds minus the starting 1 second. Okay, so we already did F of 2 a minute ago. That was 64. Now F of 1, that would be 16 times 1 squared. And then on the bottom, 2 minus 1. So that's going to be 64 minus 16 over 1, which gives us 48 over 1, or 48 feet per second. So now what we're ready to actually figure out, what about at a very specific moment in time? What is the speed at that time? And we would call that the instantaneous speed. Okay, so how would we calculate that? Notice that on our 2-second interval, when we said from 0 to 2, we got 32 feet per second, and then on our 1-second interval, we got 48 feet per second. So what's actually happening at a specific second mark? So let's say maybe the 2-second mark. So what would be the instantaneous speed? We want to know at t equals 2 seconds. So the idea is that we're actually going to make the interval of time closer and closer to this number 2. So we are wanting to get like really close to 2 seconds, but we're going to kind of modify our average speed formula for the fact that we want to look at one specific second time, not more than 1 second. So here's the concept. Let's say we want to start at 2 seconds, but we actually don't want to go past it. Well, we have to kind of get there with this idea. Let's say that our stopping time is really, really close to the 2-second mark. So maybe it's 2.1 seconds. Okay, well that's close, but can we get closer? Okay, maybe we can go 2.01. That's way closer to 2 seconds. Well, we can go even closer and say 2.001 and so on, and get so close to our specific time value that it's looking at that instant in time. And so our formula is going to get modified. We can write it like the change in idea. Delta is the change, so change in the distance over the change in the time. And on top we had f of t2 minus f of t1. Well, our f of t2, we'll fill that in a moment. F of t1 is our specific second in time that we're looking at. So what's happening is we're just actually looking really, really close to that number. So we are looking at f of t, but maybe a little tiny bit more. So we're going to say plus a little bit more. So this idea of plus h is a very, very small number that's eventually trying to just become nothing. So it's approaching 0. Alright, so the f of t is our starting position, and f of t plus h is our stopping position, which is something very, very close to the starting position, so much so that it is the same position because we're looking at a specific instant in time. So on bottom, t2 would be t plus h minus t1, which is just t, and this simplifies to h on bottom. So we have this modified version of the formula, which actually ends up giving us instantaneous speed. Okay, so let's look at what happens here with this example. Alright, so what is the instantaneous speed at the 2-second mark of this falling object? So we have f of 2 plus h minus f of 2 over h. Okay, so h, we know that we want it to approach 0, so the idea here is actually a limit idea. And so you could say as h approaches 0, and the same way to say that is you say that the limit of this function as h approaches 0. Okay, so h is getting really, really close to 0, which is this idea here where you're going closer and closer to the change from 2 to 2.1, 2.01, 2.001 is so small, it's like 0. Okay, so we know what f of 2 is. We can work this out. Let's ignore the limit in the front. Basically, at the end, we're going to be able to just plug in 0 for h. But look, right now we can't, because if we put a 0 in here, then we'd be dividing by 0. So that doesn't work. So we cannot put a 0 there right now. So what we have to do is simplify this a little bit algebraically. So we have a formula, if you recall, and I'll write it here. Our free fall of our object was given by the position 16t squared. Okay, so we're going to use that. So we have f of 2 plus h. So that's taking the place of t, your input. So our input is going here, it's getting squared, and it's getting multiplied by 16. So the input, 2 plus h, just goes right in that position where t was. Okay, so 2 plus h goes there, and let's just keep this all together. So that was f of t plus h. If we go right here, that was the top of our formula. That was what was f of t2 originally. So now we say minus f of t1. So minus, and we have f of t1 is just f of 2. We did that one already a number of times. That was 64. And then h again is just on the bottom, but we can't plug in 0 right now. The limit is technically still there in front, but I'm just ignoring that until we're ready to plug it in. And so we're going to say that if we work this out, we'll expand if you say 2 plus h. So if you need to, you can do some side work on the 2 plus h quantity squared. So you would FOIL this out. You would say 2 times 2 plus 2 times h plus another h times 2. Expand that out. And so we'd have 16 times 4 plus 4h plus h squared minus 64 all over h. And if you distribute that 16, we're going to get 64 plus 64h plus 16h squared minus 64 all over h. If we factor out an h from the top, h times 64 plus 16h all over h. And now because we're dividing and multiplying, h times something divided by h, that's the moment when we get to divide these out. And so because h over h is just 1, so those go away. And so now here's the concept. We're going to put this limit back on. The limit as h approaches 0 is saying if h gets really, really close to 0, this change h, then what happens here? And so at this moment we are just able to plug this in. So we can just put 0 right here. That gives us 64. So 64 feet per second is our instantaneous rate of change. At the instant, 2 seconds in this example, rate at which that rock was falling was 64 feet per second. Alright, so we're ready to bring it all together. So what we have is our average rate of change formula now. Earlier we technically called it average speed, but we can use this idea of picking a value really, really close to our second point and changing our second input for that. So what I'm saying is t1 and t2. We can generalize this for any functions. So x1 is the starting value and x2 is where we would stop. And so we have our average rate of change formula, the change in the output over the change in the input. If we pick values really, really close to x1, we can say that that's x1 plus some h value. And so instead of calling this as something separate like x2, it's just a little bit more than x1. So this is our modified formula, and this is our average rate of change. And what this actually gives us is the slope to what's called a secant line. So if we consider this blue curve, so the blue is the function we are interested in, and we want to kind of know like the rate at which that function is changing. Well, we can pick 2 points on the curve, and that will be our x1 and our x2. And then we plug those into our average rate of change formula. That gives us the steepness or the slope of this line between the points, and that line is called a secant line. Okay, a line between 2 points on a curve like this is a secant line. So the average rate of change gives you the slope to the secant line. So now if you imagine we want to make this number h smaller and smaller, and we want to get closer and closer, our points should be closer and closer together, so much so that they basically become a single point. So we would say, okay, I don't want my points so far apart. Maybe my x1 is still where it's at, but x2 is even closer, and so that would be right there on the curve. Or maybe I want to go even closer, like right there and right there, and eventually you're just zooming in so close to a single point, and that's what is then going to become a tangent line. So when your points get closer and closer together and they become a single point, then all of these are secant lines, and then it becomes a single tangent line. So when you have a curve, so let's say this is our blue curve, and our 2 points on our curve get closer and closer and closer together until there's a single point, then that is our tangent line at that point. And so what the tangent line at a point gives us is it actually gives us the slope or rate of change at that point, which is an instantaneous rate of change. So the slope of the tangent line is equal to our instantaneous rate of change. And so we basically take our average rate of change formula and we just adjust it slightly by considering that that h value, that number that's telling us our points are really close together, we add the limit as h approaches 0, and we just put that in front of our average rate of change formula to give us an instantaneous rate of change. So these slopes are our rates of change. Slope of a secant line, once again, is the slope between 2 points on the curve and the line going through those 2 points. And then the slope of the tangent line is slope of the line where it's approximating the curve steepness or rate of change at that single point. And if you are actually wanting the equation of the line, then you just go to your algebra and you say the equation of a line formula. And so we have y minus y1 equals m times x minus x1. And so as long as you know a point on the line, okay, so if you're wanting the equation of a secant line or equation of a tangent line, the point x1, y1 in this formula is a point on your line. And then m is your slope. And so the slope is, if this is a tangent line, it's your instantaneous rate of change. And then you would just calculate that value based on our formula here, and then you could plug that in and find your equation of your tangent line. All right, that's it for this one. Thanks for watching.